Learning objectives. In this chapter, the user would learn the following in detail. Overview of computer organization, logic gates, adders, flip-flops as 1-bit memory device, encoders, decoders, multiplexers, registers, shift registers, counters, RAM, ROM. Computer organization. Way the hardware components operate. Way they are connected together to form the computer system. Hardware is the actual physical component of the computer. Architecture is the design of the layout and connectivity of these hardware components. Basic computer concepts. A digital computer is a programmable machine that processes binary data. A computer has 4 basic units, namely input unit, central processing unit, memory unit, and output unit. Input unit. A computer accepts digitally coded information through input unit. The input unit consists of one or more input device. Example, keyboard and mouse are the most commonly used input devices. Central Processing Unit, CPU. It interprets the instructions in the program and executes one by one. It consists of 3 major units. Control unit. It controls and directs the transfer of program instructions and data between various units. Arithmetic operations like addition, subtraction, multiplication to the power of, division. Logical operations like and, or, not, and relational operations like lesser than, greater than, lesser than or equal to, greater than or equal to, are being carried out in this unit. Memory unit. It is used to store the programs and data. Output unit. It is used to print or display the results which are stored in the memory unit. Logic gates. Introduction. Manipulation of binary information is done by logic circuit called gates. Gates are the block of hardware that produce signal in the binary form 0 or 1. A gate is simply an electronic circuit. This operates on one or more input signals representing 0 or 1 to produce an output signal. These gates are the basic building blocks for digital design. Each gate is built up from a small number of transistors. Gates are the fundamental component in digital logic circuits. Gates are constructed from elementary electronic components, transistors and resistors. Logic gate is an electronic circuit, is also called as switches. Logic gates have no memory. There are a number of gates which were used to design a digital circuit. The basic gates are inverter or not, and or. Inverter or not gate. The inverter not circuit performs a basic logic function called inversion or complementation. Inverter is to change one logic level, high or low, to the opposite logic level. In terms of bits, it changes a 1 to a 0 and vice versa. The standard logic symbol and truth table for the inverter. The AND gate. The AND gate, which is composed of 2 or more inputs and a single output, performs logical multiplication. The logical operation of the AND gate is such that the output is high, 1, when all the inputs are high. Otherwise, it is low, 0. The standard logic symbol and truth table for the AND gate. The OR gate. The OR gate, which is composed of two or more inputs and a single output, performs logical addition. The logical operation of the OR gate is such that the output is high, 1, when any of the inputs are high. Otherwise, it is low, 0. The standard logic symbol and truth table for the OR gate. The NAND gate. The NAND is complement of AND function, not AND. The logical operation of the NAND gate is such that the output is low, 0, only when all the inputs are high, 1. It is a very popular logic element because it may be used as an universal function. The term NAND is formed by the concatenation of not AND and implies an AND function with an inverted output, graphically represented as an AND gate followed by a small circle. The standard logic symbol and truth table for the NAND gate. The NOR gate. The NOR is complement of OR function, not OR. The logical operation of the NOR gate is such that the output is high, 1, only when all the inputs are low, 0. It is a very popular logic element because it may be used as a universal function. The term NOR is formed by the concatenation not OR and implies an OR function with an inverted output, graphically represented as an OR gate followed by a small circle. The standard logic symbol and truth table for the NOR gate. The exclusive OR XOR gates. The exclusive OR is an inequality function and the output is high, 1, when the inputs are not equal to each other. Example of XOR gate. The standard logic symbol and truth table for the XOR gate. Exclusive NOR XNOR gates. Conversely, the exclusive NOR is an equality function and the output is high, 1, when the inputs are equal to each other. Because of their functional importance, these gates are treated as basic gates with their own unique symbols. Example of XNOR gates. The standard logic symbol and truth table for the XNOR gate. Logic circuit. Group of gates used to manipulate the binary logic data is referred to as a logic circuit. The truth tables for logic circuits are constructed by applying each of the possible n equals 2n input combinations to the circuit inputs and determining the corresponding output. Combinational circuits. A combinational circuit is a connected arrangement of logic gates with a set of inputs and outputs. A well-formed combinational circuit should not have feedback loops. The output of a combinational circuit is related to its input by a combinational function which is independent of time. Therefore, according to input given, the output is changed. The n binary input variables come from an external source. The m binary output variables go to an external destination, and in between there is an interconnection of logic gates. Design process. The design of combinational circuit can be carried out in the following 5 steps. The problem is stated. The input and output variables are assigned letter symbols. The truth table is used to define the relationship between the input and output variables. The Boolean function for each output variable is derived. The logic diagram is plotted. Equivalent circuits. The NAND and NOR were universal logic gates. Using De Morgan's theorem and the rules and laws of Boolean algebra, proving this should be an easy task. Shows the equivalency between the basic logic gates and their NOR logic circuits counterpart. Adder. Adder is a combinational logic circuit that performs the additions of two or more logical bits. Half adder. This combinational circuit performs the arithmetic addition of two input bits. Design of a half adder. A binary half adder is a switching circuit which will add together two binary digits called binary bits, producing two output bits, a sum bit S and a carry bit C. A half adder is used to add two bits. The result consists of two bits, a sum, the right bit, and a carryout, the left bit. Input A and B is 0, sum equals 0, and carry equals 0. Input A equals 0, B equals 1. Output is sum equals 1 and carry equals 0. Input A equals 1, B equals 0. Output is sum equals 1 and carry equals 0. Both input A and B is 1. Sum equals 0 and carry equals 1. Full adder. A full adder is a combinational circuit that forms the arithmetic sum of three input bits. Design of a full adder. A binary full adder is a switching circuit which will add together two binary digits called binary bits and a third bit called a carry bit, which may have come from a previous full adder. It produces both a sum bit and a carry bit as output. The full adder therefore has three inputs, A, B and C in, where C in is the carry bit. Two outputs, the sum S and the carry count. It is possible to connect n such full adders together to add two n-bit numbers. Flip-flops. Flip-flops as one-bit memory device. Flip-flops are synchronous stable storage devices capable of storing one bit, either 0 or 1. Synchronous means that the output state only changes at a specified point on a triggering input called the clock C. That is, the output changes are synchronized with the clock signal. Latches are level sensitive or level triggered. This means that the outputs are dependent on the voltage level applied, not on any signal transition. Flip-flops are edge-triggered. That is, that they depend on the transition of a signal. This may either be low to high, rising edge, or a high to low, falling edge transition. Design issue. When using logic symbols, edge triggering is indicated by a small triangle inside the block at the clock input C. The absence or presence of a bubble outside the block is used to indicate rising and falling edge triggering, respectively. The logic symbols illustrating these concepts are shown. Types of flip-flop. Sequential circuits use flip-flops as storage elements. Flip-flop is a binary storage device that saves one bit of information. The outputs can come from flip-flops or Combinational logic. Flip-flop inputs come from combinational logic or clock generators. Different flip-flops are different based on the number of inputs and how the inputs affect the binary state. Basic types of flip-flops operate with signal levels and are called latches. Example, SR latch. A basic flip-flop can be constructed using two NAND or NOR gates. It contains a feedback loop. The circuit shown is a basic NOR latch. The inputs are generally designated S and R for set and reset respectively. For the NOR latch circuit, both inputs should normally be at a logic 0 level. Changing an input to logic 1 level will force that output to logic 0. The same logic 0 will also be applied to the second input of the other NOR gate, allowing that output to rise to a logic 1 level. D flip-flop. This flip-flop only has one input in addition to the clock, called the D input. D flip-flop truth table. Note that whatever is on the D input when the trigger occurs is output at Q. From the truth table, it is clear that the input D is transferred to the output Q on application of a clock pulse. The output retains the previous value when the clock pulse is not applied. Edge triggered and the output changes state during the positive edge or negative edge of the input clock pulse. JK flip-flop. The JK flip-flop is perhaps the most widely used type of flip-flop. Its function is identical to that of the SR flip-flop in the set, reset and hold conditions of operation. The difference is that the JK flip-flop does not have any forbidden states. JK flip-flop truth table and JK waveform diagram. Notice that for J equals 1 and K equals 1, the output toggles. That is to say, the output at time t is complemented at time t plus 1. Let us now examine the output waveforms from the JK flip-flop given the input shown in figure. Assume that Q is high initially. Flip-flops with asynchronous inputs. Most integrated circuit flip-flops also have asynchronous inputs that affect state of the flip-flop independent of the clock. These inputs are normally labeled preset (PRE) and clear (CLR) by the manufacturers. An active level on the preset will set the flip-flop 1. Similarly, an active level on the clear will reset 0 the flip-flop. The logic symbol and the operation of a positive edge triggered JK flip-flop with active low preset and clear inputs are shown in figure respectively. Note that we assume Q is high initially. Pulse-triggered master-slave. The second class of flip-flop is the pulse-triggered or master-slave. These flip-flops are constructed from two separate flip-flops. The term pulse-triggered means that data are entered into the flip-flop on the leading edge of the clock pulse, but the output does not reflect the input state until the trailing edge of the clock pulse. This is due to the master flip-flop being rising edge triggered and the slave flip-flop being falling edge triggered as illustrated in figure. The logic symbol for the master-slave flip-flop only indicates the initial inputs to the master and the outputs from the slave as indicated by the JK master-slave flip-flop shown. T flip-flop. The T-type flip-flop is a single input device, T-trigger, two outputs, Q and Q dash, where Q dash is the inverse of Q. The operation of the T-type flip-flop is as follows. A 0 input to T will make the next state the same as the present state. That is, T equals 0, present state equals 0. Therefore, next state equals 0. However, a 1 input to t will change the next state to the inverse of the present state. That is, t equals 0, present state equals 0, therefore, next state equals 1. Knowing the above, we can now formalize the operating characteristics and the state change table. The T-type flip-flop is an edge-driven device. Therefore, you should not associate 1 and 0 with levels, but instead 1 should be considered as a pulse and 0 as no pulse. Notice that if a clock signal was tied to T, the output Q would be a clock signal at approximately half the frequency of T. This property makes the T flip-flop a good candidate for applications such as frequency division. Encoder. An encoder accepts an active level, that is 1, on one of its outputs representing a digit, example decimal or octal digit, and converts it to a coded output, example binary of BCD. The process of converting from familiar symbols or numbers to a coded format is called encoding. The decimal to BCD encoder. Decimal to BCD encoder to have 10 inputs and 4 outputs. The logic symbol for this 10-line to 4-line decoder is presented in and the associated conversion table listed in table with A3 representing the most significant bit. Truth table for decimal to BCD encoder. Decoder. Decoders can detect a code and activate a single output to signal the presence of that code. Decoders have many applications, from producing system alerts in alarm systems to performing the task of driving multiple devices in microprocessor systems, example memory. Decoders in general transform a set of inputs into a different set of outputs which are coded in a particular manner. Decoders are also available to convert numbers from binary to BCD, from binary to hexadecimal, etc. Basic binary decoder. The function of the binary decoder is to determine if a given input combination has occurred. For example, if we wish to detect that 1011 occurs on the inputs of a digital circuit, we must design a decoder which only outputs 1 for this instance. Accordingly, a 4-input AND gate and an inverter may be employed as illustrated. The 3-bit binary decoder. In order to decode all possible combinations of 3 bits, 8, 2 to the power 3 equals 8, decoding language gates are required. This type of decoder is called the 3-line to 8-line decoder because there are 3 inputs and 8 outputs. Design issue. Let us consider the design of such a decoder and assume that we require active high outputs. That is, for a given input combination, the decoder outputs 1. Such as inputs A2 equals 0, A1 equals 0, A0 equals 0. Output D0 equals 1, D1, D2, D3, D4, D5, D6, D7 equals 0. Inputs A2 equals 0, A1 equals 0, A0 equals 1. Output D1 equals 1, D0, D2, D3, D4, D5, D6, D7 equals 0. To illustrate Let's consider table shown which lists the decoding functions and truth tables for the 3-line to 8-line decoder. Decoding functions and truth tables for the 3-line to 8-line decoder. Logic symbol for the 3-line to 8-line decoder. The BCD to decimal decoder. The BCD to decimal decoder converts each BCD code to its decimal equivalent. Design issue. The technique employed is very similar to the one used in developing the 3-line to 8-line decoder. Again, assuming active high outputs are required, table given lists the decoding functions for BCD to decimal decoder. Now, we can develop a decoder based on each logic function and implement the sum of products logic circuit. This is illustrated in figure. Multiplexer. This circuit selects binary information from one of many input lines and directs it to a single output line. It has 2n inputs and 1 output. A 2n into 1 multiplexer receives 2n input bits and n selector bits and outputs exactly one of the input bits determined by the pattern of the selector bits. Selection of a particular input line is controlled by a set of selection variables or control lines. For example, a multiplexer acts like a television channel selector. All of the stations are broadcast constantly to the television's input, but only the channel that has been selected is displayed. Logic symbol for 1 of 4 multiplexer. Operation of 1 of 4 multiplexer. Demultiplexer. This circuit selects binary information from one input line and directs it to several output lines. The demultiplexer is the inverse of the multiplexer in that it takes a single data input and n addresses inputs. It has 2n outputs. Example, a demultiplexer, demux, is a device which essentially performs the opposite operation to the mux. That is, it functions as an electronic switch or data distributor to route an incoming data signal to one of several outputs. Logic symbol for 1-line to 4-line demultiplexer. Demultiplexer function tables. Registers. A register consists of a group of binary storage cells. A register consists of one or more flip-flops depending on the number of bits to be stored in a word. A register is a binary function which holds the binary information in digital form. Shift register. A register that is capable of shifting data one bit at a time is called a shift register. Serial shift register consists of a chain of flip-flops connected in cascade. The output of one flip-flop being connected to the input of its neighbor. The operation of the shift register is synchronous. Thus, each flip-flop is connected to a common clock. Using D flip-flops forms the simplest type of shift registers. Types of shift register. Basic shift registers are classified by structure according to the following types. Serial in, serial out. Parallel in, serial out. Serial in, parallel out. Universal parallel in, parallel out. Ring counter. Serial in, serial out. Above, we show a block diagram of a serial in, serial out shift register which is 4 stages long. Data at the input will be delayed by 4 clock periods from the input to the output of the shift register. Design issue. Data at data in above will be present at the stage A output after the first clock pulse. After the second pulse, stage A data is transferred to stage B output and data in is transferred to stage A output. After the third clock, stage C is replaced by stage B is replaced by stage A, and stage A is replaced by data in. After the fourth clock, the data originally present at data in is at stage D, output. The first in data is first out as it is shifted from data in to data out. Parallel in, serial out. Design issue. Data is loaded into all stages at once of a parallel in, serial out shift register. The data is then shifted out via data out by clock pulses. Since a 4-stage shift register is shown above, 4 clock pulses are required to shift out all of the data. If 4 switches were connected to DA through DD, the status could be read into a microprocessor using only one data pin and a clock pin. Since adding more switches would require no additional pins, this approach looks attractive for many inputs. Serial in, parallel out. Design issue. After the first clock, the data at data in appears at QA. After the second clock, the old QA data appears at QB. QA receives next data from data in. After the third clock, QB data is at QC. After the fourth clock, QC data is at QD. This stage contains the data first present at data in. The shift register should now contain 4 data bits. Parallel in, parallel out. A parallel in, parallel out shift register combines the function of the parallel in, serial out shift register with the function of the serial in, parallel out shift register. So, it is called as universal parallel in, parallel out. Design issue. Data presented at DA through DD is parallel loaded into the registers. This data at QA through QD may be shifted by the number of pulses presented at the clock input. Ring counter. If the serial output of a shift register is connected to the serial input, data can be perpetually shifted around the ring as long as clock pulses are present. If the output is inverted before being fed back as shown above, we do not have to worry about loading the initial data into the ring counter. Counter. A counter is a sequential circuit. A counter in principle is a register whose value is incremented by 1 on the occurrence of some event. When the value stored in counter reaches the maximum value it can store, the next incremented value becomes 0. There are 2 types of counters: asynchronous counter, synchronous counter. Asynchronous counters. Asynchronous counters do not have a common clock that controls all the flip-flop stages. The control clock is input to the first stage or the LSB stage of the counter. The clock for each subsequent stage is obtained from the flip-flop from the prior stage. A 2-bit asynchronous counter. The counter has 2 flip-flops and 2 output bits. Therefore, it is a 2-stage counter. The input clock does not trigger both flip-flops. Therefore, it is an asynchronous counter. The J and K inputs are tied together as kept high, so they are considered to be toggle flip-flops. The flip-flops are positive edge triggered. The waveform analysis reveals that Q0 is the LSB and that its frequency is half the input clock frequency. Furthermore, Q1 is the MSB and that its frequency is 1/4 the input clock frequency. The count sequence is 00, 01, 10, 11, where the LSB is Q0. Thus, it is an MOD4 binary up counter. Assume that Q0 and Q1 are low initially. Synchronous counter design. To successfully design synchronous counters, we may employ the following 6 basic steps. Create the state transition diagram. Create a present state next state table, often referred to as the next state table. Expand the table to form the transition table for each flip-flop in the circuit. The transition table shows the flip-flop inputs required to make the counter go from present state to the desired next state. This is also referred to as the excitation table. Determine the logic functions of the J and K inputs as a function of the present states. Analyze the counter to verify the design. Construct and test the counter. Step 1. Creating state transition diagram. Step 2. Creating present state next state table. Step 3. Expand the present state next state table to form the transition table. A 3-bit synchronous counter. Like asynchronous counters, synchronous counters may be designed to meet a variety of specifications. For example, decade counters that count the binary sequence 0 to 9. In addition, we may implement bidirectional counters, that is, they have the ability to count in ascending 0, 1, 2, 3, 4, 5, 6, 7, 8 and descending 8, 7, 6, 5, 4, 3, 2, 1, 0 order. In general, most bidirectional counters can be reversed at any point in their sequences. Example 0, 1, 2, 3, 4, 3, 2, 1, 0, 1, 2, 3, 4. Memory. Main memory consists of a number of storage locations, each of which is identified by a unique address. The ability of the CPU to identify each location is known as its addressability. Each location stores a word, that is, the number of bits that can be processed by the CPU in a single operation. Word length may be typically 16, 24, 32, or as many as 64 bits. Types of main memory. There are 2 types of main memory: random access memory, RAM, read-only memory, ROM. Random access memory, RAM, holds its data as long as the computer is switched on. All data in RAM is lost when the computer is switched off. Described as being volatile. It is direct access as it can be both written to or read from in any order. Most modern RAM is made from integrated circuits. Its purpose is to temporarily hold programs and data for processing. In modern computers, it also holds the operating system. Types of RAM. There are two types of RAM: static random access memory and dynamic random access memory. Static RAM is called static because it will continue to hold and store information even when power is removed. Example: magnetic core and read relays are examples of static memory. Dynamic RAM is called dynamic because it loses all data when power is removed. Example: transistors and integrated circuits are examples of dynamic memory. ROM, read-only memory, ROM. ROM holds programs and data permanently even when computer is switched off. Data can be read by the CPU in any order, so ROM is also direct access. The contents of ROM are fixed at the time of manufacture. Stores a program called the bootstrap loader that helps start up the computer. Access time of between 10 and 50 nanoseconds. Programmable read-only memory, PROM. Empty of data when manufactured. May be permanently programmed by the user. Erasable programmable read-only memory, EPROM. Can be programmed, erased, and reprogrammed. The EPROM chip has a small window on top, allowing it to be erased by shining ultraviolet light on it. After reprogramming, the window is covered to prevent new contents being erased. Access time is around 45 to 90 nanoseconds. Electrically erasable programmable read-only memory, EEPROM. Reprogrammed electronically without using ultraviolet light. Must be removed from the computer and placed in a special machine to do this. Access times between 45 and 200 nanoseconds. Flash ROM, similar to EEPROM, however, can be reprogrammed while still in the computer. Easier to upgrade programs stored in flash ROM. Used to store programs in devices, example, modems. Access time is around 45 to 90 nanoseconds. ROM cartridges, commonly used in games machines. Prevents software from being easily copied. Conclusion. In this chapter, we have covered the following aspects of digital components. Overview of computer organization. Logic gates. Adders. Flip-flops as 1-bit memory device. Encoders. Decoders. Multiplexers. Registers. Shift registers. Counters. RAM and ROM.